We're going to go ahead and take a look at limits and continuities and solve some of the problems in that area. To start with, let's take a look at what we should do in situations like if we want to find the slope s of a tangent to a nonlinear function, which we can call it a curve, at a specific point like x1 comma f of x1. We compute the following limit, which we will just abbreviate it as LIM. So in such a case, s, which is the slope, equals to limit as x move towards 0 of the function f of x1 plus h minus f of x1 over h, where x1 is just a variable, if you wish. It's not really a constant, so let's just take it as a variable other than a constant. If that is the case, then let's start by proving that limit as x goes to 0 of sine x equal to 0 and limit as x goes to 0 of cosine x equal to 1 using the sandwich theorem. To do so, let's define g of x to be equal to x minus sine x. Then g prime of x will be 1 minus cosine x. Since the only values for which g prime of x equals to 0 are the values when x equals to n times pi, where n is any integer in the interval 0 to infinity. For non-integer values of n, g prime of x will always be greater or equal to 0. Therefore, the function g of x is always greater or equal to 0 implies the absolute value of x always greater or equal to sine x, and sine x always greater or equal to the negative value of absolute value of x. Therefore, if we take the limit of the absolute value of x as x goes to 0, that will give us 0. And also, if we take the limit as x goes to 0 of the negative of the absolute value of x, that will also give us 0. Since both of them give us 0, that implies that limit as x goes to 0 of sine x equal to 0. Now we can see this on these three graphs. We have three graphs, one in purple, one in blue, and the other one is yellowish brown probably. If we take a look at the top one, which is a graph for absolute value of theta, we will see that it's always greater than the values of y equal to sine theta. And if we take a look at the graph of y equal to the negative of the absolute value of theta, we will also see that all its values are less than the values of y equal to sine theta. The only point where the three values will all be equal is at 0. So what does that mean? That means if we take the limit from the left or from the right of the absolute value of theta as theta goes to 0, that will be equal to 0. And if we take the limit from the left or from the right of the function y equal to negative absolute value of theta, we will see that the limit is going to be equal to 0. That implies that the sandwiched function, which is y equal to sine x, also has a limit when theta goes to 0 that will be equal to 0. So that takes care of the first part. Let's take a look at the second part. The second part, which is proving that cosine theta, cosine x as x goes to 0 is going to be equal to 1. And we're using x, but in the figures we're using theta. It doesn't matter. Anyway, the concept is what is more important. Now, so to prove that the limit of the cosine of an angle equal to 1 when the angle moves to 0, we're going to go ahead and define h of x equal to x minus 1 plus cosine x, and then we will take the derivative of h of x. So h prime of x will be equal to 1 minus sine x. This is greater than or equal to 0 all the time. Thus, h of x will be greater or equal to 0, implies the absolute value of x is greater or equal to 1 minus cosine x greater or equal to 0. Therefore, if we take the limit of the absolute value of x as x moves to 0, and that it is obviously equal to 0, and also the limit of the function f of x equal to 0 as x goes to 0 is also equal to 0, we can also conclude that limit as x goes to 0 of 1 minus cosine x will also be equal to 0. Let's take a look at the graphs. We have also three graphs. The one in purple is a graph for y equal to absolute value of x. The one in blue is y equal to 1 minus cosine theta, and the one in yellow is y equals to 0. So we can see that if we take the limit as theta goes to 0 of the yellow graph or of the purple graph, we can see that their limit as theta goes to 0 will always be equal to 0. That implies that the limit as theta goes to 0 of the blue graph, the limit will also be equal to 0. That implies that 1 minus cosine theta equal to 0 as theta goes to 0. Then we can see that limit of cosine theta as theta goes to 0 will be equal to 1, and that proves the last part that we want to prove. Next, we have to find the average rate of change of a function over a given interval or intervals. Take a look at the function g of t equal to 2 plus cosine t. We're going to find the average rate of change of this function over the interval 0 pi and over the interval negative pi comma pi. To find the average rate of change of a function, we have to find its derivative. So assuming that g prime of t is a derivative, it will be given by limit as h goes to 0 of g of t plus h minus g of t divided by h. And now we could just replace g of t plus h by its value, and that's equal to 2 plus cosine t plus h, and replace g of t by its value, which is equal to 2 plus cosine t divided by h. Now we have to expand cosine t plus h, and we do that in the next step. In green is expansion, and from this expansion we can see that we can eliminate the 2 by the 2 at the end, because we have plus 2 at the beginning and we have minus 2 at the end, so the 2 is going to go, and then we will be left with limit as h goes to 0 of everything else is the same, identical as this function. The only thing is that the 2 is removed from the first term, so the 2 in the beginning and the end are removed, everything else is the same. But also we colored cosine t at the beginning and cosine t at the end, we colored them with the same color, brown color, because we want to group them together. If we group these two together, we're going to get cosine t multiplied by cosine h minus 1. We group this along with cosine t multiplied by cosine h. The grouping will give us cosine t multiplied by cosine h minus 1. And then the middle term will be the last term, which is minus sine t sine h divided by h. Now we have to find the limit of this. And to do so, we could go ahead and take cosine t outside the limit, because this limit applies to everything inside. So to apply the limit to this part, the right hand side, we have to take cosine t outside, because cosine t is not impacted by the limit. And then we have to take the limit of the factor of cosine t, which is this value. So we have limit as h goes to 0 of cosine h minus 1 divided by h. And then minus, we have to apply the limit also to the last part of this numerator, which is sine t sine h. But sine t is not impacted by the limit, so we're going to take sine t outside, and then we'll take the limit of sine h divided by h. We know that sine h divided by h, the limit of sine h divided by h as h goes to 0 is equal to 1. That means we will reduce the left hand side to the right hand side. The right hand side is identical to the left hand side, except that we eliminated the limit as h goes to 0 of sine h over h, because that's equal to 1. So now we have to work on this one and figure out this limit. And to do so, we're going to go ahead and use a trick. What we'll do is we'll multiply the numerator, cosine h minus 1, we multiply it by cosine h plus 1, and we multiply its denominator by cosine h plus 1. So this is cosine h plus 1 multiplied by the numerator, and cosine h plus 1 multiplied by the denominator, which is h. Now, the multiplication of the numerator will result in cosine square h minus 1. Multiplication of the denominator will result in h multiplied by cosine h plus 1. So this is h multiplied by cosine h plus 1. The next term is just minus sine t. So since this is minus sine t, we'll just put it there, minus sine t. Now we have to work on this part of the limit to figure out this limit. We have to first of all figure out the identity of cosine square h minus 1, because we need to get rid of this h. And to do so, we could just go ahead and replace cosine square h minus 1 by sine square h. So we replace cosine square of h minus 1 by sine square of h. The rest is the same. The denominator is the same, and the last term is the same as this. Now we have to split sine square h into two values as follows. The first value, we're going to take the limit as h goes to 0 of sine h over h. So the first sine h, we pair it with the denominator h, and we take the limit. So limit as h goes to 0 of sine h divided by h. The second sine h, we'll group it with the denominator that contains cosine h plus 1. So this will be limit as h goes to 0 of sine h divided by h, multiplied by limit as h goes to 0 of negative sine h divided by cosine h plus 1. One more time. These two denominators, if we multiply them together, they will give us the denominator over here. And the numerators, if we multiply them, they will give us negative sine square h. Now we will go ahead and eliminate this limit of h goes to 0 of sine h over h. This will give us 1, so this is gone. And then now we have limit as h goes to 0 of negative sine h divided by cosine h plus 1. And then this is minus sine of t. Now if we apply the limit, then we know that limit of sine 0 is going to be equal to 0. And then the denominator will be equal to 1 plus 1, which is 2. So 0 divided by anything is 0. This term is gone. The only term that is left for us is minus sine t. Since minus sine t is the only term that's left for us, and we have in colors the values. The value of this term is 1, the value of the red term is 0, and minus sine t remains the same. So in the end we have 0 minus sine t. So the answer is really the limit is equal to minus sine t. And if we just do regular derivative, then derivative of the right hand side will be 0 plus the derivative of cosine t is equal to negative sine t, which is the same result that we reached. Therefore, the average rate of change of the function g of x is 0 for case A, and it's also 0 for case B. And that's it for this. This problem is about finding the average rate of change for the function r of theta over the interval 0 and 2. So to start with, we have to know r of theta. So r of theta is equal to square root of 4 theta plus 1. So to get the rate of change for r of theta, we have to do the derivative of r of theta. So represented by r prime of theta, the derivative will be equal to limit as h goes to 0 of r of theta plus h minus r of theta divided by h. R of theta plus h is equivalent to the square root of 4 theta plus 4h plus 1. And r of theta represented by its value, which is square root of 4 theta plus 1. Now that we have the square roots involved in this part, so we have to use the conjugate to get rid of the square roots. And to do so, we have to multiply the numerator by the conjugate and the denominator by the conjugate, and that's what we're going to get. So the limit of as h goes to 0, and this is our original function, its numerator is multiplied by its conjugate, and the same conjugate is multiplied by the denominator, which has h only. If we do the math, we're going to get limit as h goes to 0, and on the numerator we will have, after we do the multiplication, we will have 4 theta plus 4h plus 1, and then we have to subtract from it 4 theta plus 1. So we can see that the 4 theta plus 1 here will cancel the 4 theta plus 1, and we'll end up with 4h on the numerator. The denominator will remain the same, h multiplied by the conjugate, and that's going to give us 4h divided by h multiplied by the conjugate. We can just get rid of the h in the numerator and the h in the denominator, and we'll end up with 4 divided by the conjugate. And now if we apply the limit as h goes to 0 by replacing h by 0, we will replace this 4h by 0, and we'll end up having 4 divided by square root of 4 theta plus 1 plus the square root of 4 theta plus 1, and that will give us 2 multiplied by the square root of 4 theta plus 1. And if we involve the 4, then we will reduce the expression to 2 divided by the square root of 4 theta plus 1. Now we want the rate of change over this interval. That means we have to evaluate this limit between 2 and 4. And evaluation between 2 and 4, we start with 2. 2 times 4 is going to be equal to 8. So we'll have 2 divided by the square root of 8 plus 1. And then we replace theta by 0. That's going to give us 2 divided by the square root of 1. And that's equal to 2. So this is minus 2. So evaluation between 2 and 0 of this value is going to give us 2 divided by the square root of 9 minus 2, and that's going to give us 2 divided by 3 minus 2, and that will be equal to negative 4 over 3. That's it for this problem. Let's take a look at the next problem. Next, we have to find the equation of the tangent to the function y equal to x squared minus 2x minus 3 at the point P with x value 2 and y value negative 3. So to start with, let's find the derivative of the function y, which will denote as y prime equals to limit as x goes to 0 of x plus h squared minus 2x plus h minus 3 minus x squared minus 2x minus 3 all divided by h. Now we will expand x plus 1 squared. We will get x squared plus 2xh plus h squared minus 2x minus 2h minus 3 minus x squared plus 2x plus 3. We can cancel plus 3 with minus 3. We can cancel plus 2x with minus 2x, and we can also cancel negative x squared with positive x squared. So we'll end up having the limit as follows: 2xh plus h squared minus 2h divided by h. We can see that each and every term in the numerator has h as a factor, so we could just factor out x. If we factor out h, then the h will cancel this h, and the numerator will be 2x plus h minus 2 divided by 1. One more time, we can factor out h, and then that h in the numerator will cancel the h in the denominator. We end up with the denominator equal to 1, and numerator is 2x plus h minus 2. Now if we apply the rule, we will evaluate h by 0, replacing h by 0, and that's going to give us 2x minus 2, and that is the equation of the derivative of y, which is y prime. Therefore, the slope m at p of 2 comma negative 3 is given by evaluating the derivative at x equals to 2, and that will lead us to m eventually equal to also 2. Now, since we're looking for the equation of the tangent is a straight line, and normally the general formula for a straight line is mx plus b, so we call the tangent g of x equal to mx plus b. The only thing that we don't know is b. We know x to be equal to 2. We know the slope m to be equal to 2. So we will just plug in for x 2, and that will lead us to evaluating or finding out the value of b. So negative 3 is the value of g of x. G of x at x equal to 2. G of 2 is equal to negative 3. So negative 3 is equal to m equal to 2 multiplied by x equal to 2 plus b. And if we do the math, there will be a 4 here. We'll take it to the other side. It will be negative 4, and we have negative 3. So negative 3 minus 4 is minus 7, or negative 7. So b will be equal to negative 7. And then, of course, consequently, we can say that g of x equal to 2x minus 7. And that ends the proof, or that ends finding the equation of the tangent. Next, we're going to have to find the limits of the function g of x, which is a piecewise function, as we see over here. We want to find the limits of the function when x approaches 1, and when x approaches 2, when x approaches 3, and when x approaches 2.5. So let's take them one at a time. For part A, we want x approaches 1. So we can see that the function g of x, if we approach 1 from the left, the limit will be equal to 1. If we approach 1 from the right, the limit will be equal to 0. So there's the jump here, so the limit does not exist for x approaching 1. And this is the answer. The limit does not exist, D and E, because the limit from the left is not equal to the limit from the right for x equal to 1. Let's take a look at part B. Part B is about finding the limit of g of x as x approaches 2. We can see that x approaches 2 from the left and from the right. And both of them, the limit is going to be equal to 1. The limit of g of x as x approaches 2 from the left is equal to 1. And the limit of g of x as x approaches 2 from the right is also 1. So the limit exists and the limit equals to 1. And also the function evaluates at 2 will give us 1 as well. So the answer is the limit exists. That is the limit as x approaches 2. The limit exists and equals to 1 because the limit from the left equals to the limit from the right equals to g of 2 equals to 1 as we said. Next we have to look at part C, which is for the limit as x approaches 3 of g of x. We can approach 3 from the left and the limit will be 0. We can also approach 3 from the right and the limit will also be 0. So the limit does exist and it's equal to 0. And this is the answer. The limit exists and equal to 0 because the limit from the left equals the limit from the right. The next part, D, we have to look at the limit of g of x as x approaches 2.5. So we can see that we don't see any mark that tells us the value of the function g of x at 2.5. So we have to look into this triangle for a solution. We can see that this line has a slope of 1. And this line is parallel to this line, so it also has a slope of 1. Since this has a slope of 1, this line will have a slope of -1. So now we know the slope of this line to be -1. We could go ahead and look at the function now. The function g of x is a piecewise function, and in the interval 2, 3, g of x equal to -1 times x plus b, because it is a straight line, and this is the general formula for a linear function or a straight line, where -1 is the slope here and x plus b are the variables. So g of x equal to minus x plus b. We have to figure out the value of b, where b is the y-intercept. The function does not have y-intercept, but theoretically, if it continues moving that way, the y-intercept will be equal to the value that we're going to compute, and we're going to consider it. So it's not going to be any problem. So now that we decided that g of x, this section of the function g of x between 2 and 3 has an equation g of x equal to -x plus b. So since we are looking at this point 3, we can evaluate and find out the value of b as follows. Evaluating g of x at x equals to 2 gives us g of 2 equal to 1. And we know that g of 2 is equal to 1. So since g of 2 is equal to 1, therefore g of 2 equals to minus and then 2 for x, minus and then 2 for x, where minus is coming from the slope, -1. So -2 plus b. But we know that g of 2 is equal to 1. So if we take -2 to the left hand side, where g of 2 is equal to 1, that will give us 3. So this equation implies that b is equal to 3. Now that we know b equal to 3, then the equation of g of x is going to be g of x equal to -x plus 3, where 3 is the value of b. Now that we have g of x, which is the equation of the section of g of x between x equal 2 and x equal to 3, we can evaluate the function at 2.5. So we will look at g of 2.5 and we'll plug in here 2.5 to find out the value of g of 2.5. And if we do the math, we can have g of 2.5 equal to negative 2.5 plus 3, and that's equal to 0.5. And that is the answer for this part. Now we have to find for the function f of x, which is a piecewise function graphed right there. We need to find the following limits or explain why they do not exist. A, we want to find the limit of f of t as t approaches negative 2. We can see that t approaches negative 2 from the left and from the right. And for that reason, the limit exists, and the limit is equal to 0, because the limit as we approach negative 2 from the left is 0, and the limit as we approach negative 2 from the right also is equal to 0. So the limit exists and it's equal to 0. That's the first part. The second part, part B, we want to see the limit as t approaches negative 1. We can see that t approaches negative 1 from the left will give us the limit as negative 1. Also, t approaching negative 1 from the right will also give us the limit equal negative 1. So in both cases, the limit equals to negative 1. So the limit exists and the limit equal to negative 1. Part C, we want the limit of f of t as t approaches 0. We can see that we can approach 0 from the left and from the right. If approach 0 from the left, the limit will be equal to negative 1. If approach 0 from the right, then the limit will be positive 1. Since there is a jump over here, so the limit does not exist. And f of 0 is equal to 0, but the limit does not exist. So limit f of t as t goes to 0 does not exist, D and E, because the limit from the left does not equal to the limit from the right. Part D, we have to find the limit as t approaches negative half of f of t. So t can approach negative half from the left, and when approaches negative half, the value of the limit will be negative 1. When we approach negative half from the right, the value of the limit will also be negative 1. So in both cases, the value of the limit exists as t goes to 0.5 and its value is equal to negative 1. And that wraps us this part.